I have no idea what's on them. Yeah, I don't know what you're rating me on, but
Chill it.
So as Grant mentioned, I am an engineer, and I'll talk a bit about what I do and all that kind of stuff, a bit about engineering itself. But yeah, I mean, the real value in this, though, is in the questions you ask, so just kind of try to have those go in your head as I'm going through this. And as you can tell from this picture, the engineering I'm in is something to do with boats, so I'll get into that as we go. So what is an engineer? I know actually when I was in high school, I wanted to be an engineer, but actually looking back, I had no idea what engineering was. So I don't know if that's any of you guys. Do you guys have any interest in, well, it's an unfair question to ask right now, but you guys interested in being an engineer, like one day, kind of pursuing that path in high school? Anyone thought about engineering? Okay, good. We've got one clear path. So anyway, so a few definitions of engineers that as engineers we like to kind of laugh at. So an engineer, an organism who solves problems you didn't know you had in a way you don't understand. Another one would be a person who performs precision guesswork based on unreliable data, provided those of questionable knowledge, or kind of like wizards. In reality, this is probably the closest to reality. So a person who uses science to solve practical problems. So that could be pretty much everything in modern society. So let's see how this cable holds up. So from building ships to designing cars, or there should be another picture that show up. Anyways, there's a bridge in there, but pretty much anything in modern society. So buildings, bridges, ways of transportation, energy generation, so power plants, all that kind of stuff, all getting designed by engineers. Your phones. Yeah, it's pretty much you have engineers in everything. So specifically the type of engineering I do is naval architecture, so we do ship design. The company I work at mainly does tugboats or workboats, so like icebreakers, offshore supply vessels, fireboats, all that kind of stuff. The company I work for is called Robert Allen Limited, so they're located in Vancouver. We're pretty much the oldest naval architecture company in Canada, possibly North America. We're founded in the 1930s. And we probably design maybe about half of the world's tugboats, so we're probably one of the biggest tug designers in the world, and we're only 85 employees, which kind of shows the market is actually pretty small for tugs. So naval architecture, kind of what is naval architecture in a nutshell? So essentially naval architecture is the design of ships, but it's essentially everything that you see when you look at a boat. So how it looks, the shape of the hull, where everything is on it, so essentially where all the cabins are and the engine room and all that kind of stuff. So it fills its main purpose. Stability, so in naval architecture, stability is just the science of the engineering of making sure a boat doesn't flip over. So you've got a boat out there, obviously you want to make sure it doesn't capsize. There were definitely some ships made a long time ago. I think there's a warship made in Sweden a while ago that they spent ages building it. It cost a fortune to build. They launched it, and right when it launched, it just flipped over. So it's a very important thing to get right. So as engineers, we work on that. Structure as well. So when you build these boats, you have to make sure they won't just break apart just due to the loads they have. So it sounds obvious, but sometimes it's a bit hard to do. So marine engineering is the other part of any naval company. So naval architecture, all the looks and all the layout and all that good stuff. Marine engineering is all the guts. So essentially all the fluids inside, lubrication, fuel, HVAC, so the heating and ventilation, engines, propulsion, all that kind of stuff. So there are a few videos in here which I don't know really work, and you can always skip past them if they don't really work. And it doesn't matter if there's not much audio, but essentially this was, I guess, one of our boats that was featured on some Mega Machines TV program in the States. So these couple fireboats, which I guess hopefully you'll see in a few clips here, are, I think they're probably the most powerful fireboats in the world, but they service Port of Long Beach, which is a container port in western United States. I think it's probably one of their biggest container ports. They do about $1 billion a day of trade. So anytime they have a fire, if it shuts down the port for a day, that's $1 billion out the window. So they have these massive fireboats that essentially can put out anything. I think they can pretty much put out a fire 20 stories up in the air, pretty far away. So this is another fireboat that we've done. So this is for the New York Fire Department. And this one might not be as powerful as the one on the West Coast, but essentially the Fire Department of New York came to us and said, "It was the biggest fireboat in the world, and we want ours to be 1 foot bigger." essentially just the American way of things. But so this one was kind of done in homage to September 11th. So it's made of steel from the towers, I think, that came down. So now the boats we design, icebreakers, so ones that just work up in the north. I think that's servicing an oil rig up there. And the one on the left is a harbor tug. The one on the right is like a training tug, but essentially it's a whole range of ships. We're also getting into autonomous, and this is kind of going to be your guys' thing if any of you go into engineering. It's just more and more things are going to be robotic, autonomous, remote controlled, and have all these ships going around with no one on them. So what do we do? I mean, it's a bit hard to conceptualize right now if you guys are familiar with engineering, but a couple of things we deliver as engineers is 2D packages. So essentially, it's pretty old school, so it's just drawings. So just paper drawings that a shipyard can turn into a boat. So we deliver like a fat stack of just drawings showing every aspect of how to build the boat, and the shipyard would take that, scale it way up to full scale, and then actually build the boat. So this is just one sample of a drawing that we'd make, but there'd be hundreds of drawings in kind of a package that defines one boat. 3D modeling we do as well, so these are all, obviously not photos, all just 3D renderings. And so we can actually fully kind of get a picture of what the boat actually looks like before we build it. And then the client can be happy as well. So propulsion as well, so we'll work on this, so actually sizing the drives. I mean, that's kind of, I guess those propellers up on the top left is kind of typical size that we deal with. So yeah, all pretty massive equipment. And stability, like I mentioned before, so we have to work on these boats to make sure that any weather conditions they're in, most ways they can drive them, that they're not going to flip over and kill themselves. So it's definitely a critical, important part. So my job, so that's the overall naval architecture field in a nutshell in a very short period of time. So my job is specifically in something called computational fluid dynamics, which sounds like a mouthful, but all it really is looking at the fluid flow. So essentially just how the boat moves through the water. So how does it move through the water? Now with all the technology we have with computers, we can all predict this ahead of time in a computer. So I just end up working on a computer and simulating a boat that we've designed before it's actually built, and how it goes through the water, how much drag it has, and if you know how much drag it has, you know how big the engines have to be. So it's all kind of figuring out that ahead of time. And this is another, I think the next one's going to be a bit of a video, and it should be only a couple minutes long, but if it's dragging on, I'll switch it. But the nice thing about, I guess, this next video is that it's sped up and it shows a kind of a full job of one of these boats that we do and all the maneuvers it does, so you can kind of get a sense of what kind of things one of these boats does, and then you can get an idea of what it has to do. Yeah, sure. I mean, all there is music here to make it less boring. So, yeah, so you can. Yeah, exactly. Yeah, sure. That too. Sure. Yeah, I heard a faint audio. Yeah, and it could just be the boring. Yeah. Again. Down in Australia. So that ship right there is probably extending, what, 20 meters? So it's like 60 feet under the water. Just how much stuff it's carrying. It's carrying iron ore. Probably about like $30 million worth of iron ore. The thing on the front of the tug is really critical, so that's the winch. So it's extremely, it's probably like 400 or 500 horsepower. The thing of a car is what, 100 to 200 horsepower, so that's, I don't know, 5 times as powerful as a car, just the winch itself. That's how it attaches to a ship. And then this thing they're doing here is called indirect escort, so it's like the whole tug's acting like a wing, and it can turn the whole ship to prevent it from crashing. again, this comes back to stability. So if it's doing that, you want to make sure that that tow lines up and flip the boat over, which in some cases, on some poor boats, it's almost done. Start to movement operations. That ship's just being filled with, I don't know, like 200,000 tons of iron ore. And then the ship has to pull it off the dock and then take it out, and then as it speeds up. So this ship right now, yeah, like I mentioned, probably draws about 16 to 20 meters, and it has only maybe 20 centimeters of room underneath the ship to the bottom of the ocean. So if there's any air and it hits, then essentially the channel's blocked. And we were told that this ship grounds the country of Australia to go into recession because it would shut down their economy for potentially a couple months. It would take them that long to get the ship off the ground. So it's all like a very tight, very high stress kind of operation. So this maneuver a ship's doing right here is considered probably the highest risk in any ship maneuver. Because if the ship you're on loses power, like engine power, then you just get run over essentially by that large ship and not gonna stop. So it's one of the biggest things in design. So that's pretty much it. So getting back to kind of what we do, sorry, all this rest of it doesn't have music, but so we just take simplified models, and then this is all on a computer. And we simulate, okay, well, this is basically in waves, but then we also simulate a lot of other maneuvers, so when it's turning to the side or flipping around backwards, so we can kind of predict how it's going to perform. Yeah, we'll do higher speed boats. This is a special kind of propulsion called Voith propulsion, and instead of a normal propeller, what you think, it just looks like a bunch of egg beaters, and it's just another way of moving a ship around. So we have to also look at this case, make sure everything's designed properly and won't isn't going to break. This is, let's see. Using your imaginations.
Imagination.
Good, I'll just let all that sink in.
All those tiny men. Such a tiny boat. It's like not even, oh, that's a big boat. Tiny men. That was the first thing I used my heart.
Oh yeah.
I asked my mom 3 questions. I was like, Mom, do I have ADHD? I was like, no. I was like, am I autistic? And she's like, no. And I was like, well, am I stupid? Am I grandpa comes around and tells me yes? My mom's like, he was mad at me. And he calls me, every time I call myself stupid, my mom's like, my grandpa's like, and then my grandpa gets mad at me and he's like, Ashley, you fucking idiot. I'm like, hello?
One time I picked up your sister's headphones.
I misread the calculator.
And I picked them up and I held them up and then it was just like
I misread the calculator and I thought it was, no, we had to remember to
or just like
start.
70. And I was like, oh, are these, wait, are these all
And it wasn't. It's like this right
and looking them up, it's just like a giant one. And then I'm like, oh, I'm probably just and then it was like,
Okay.
and then she was saying that, like, she was thinking maybe they are That was a while ago.
Alright, it's good. It's giving you a chance to fill in your little yellow sheet of paper. So, anyway, so yeah, I mean, this is kind of looking at when that tug goes off to the side. So another thing we can look at in the computer is just the flow, and we look at things how the flow wraps around the hull. There's good ways it can do it, bad ways, and it kind of all works how we shape the design of the hull. This is something called, I mean, flow separation. I don't know if any of you guys are really into planes or flight simulators or any of that kind of stuff. So there's something that happens in a plane. So if it tips up and then you rise in the air because you got lift, right? So I mean, that's obviously how you fly. I'm sure most of you guys have flown. But if you go at too steep an angle, then essentially you have something called stall. So the flow breaks away and the plane will fall out of the sky and crash. same thing can happen with ships not crashing, but essentially when they turn to the side. So that's one thing we look at as well. I'll just go through these. So just to kind of change gears a bit. So that's, I mean, this in general is about engineering, specifically I do naval architecture, but I have done some other areas of engineering. Just want to share a little bit about not in the boat field. So my wife and I spent a while in Uganda working on water systems. So essentially, it was for an NGO, and then we had essentially we're doing water pipelines. So taking pipelines from up high, or sorry, water sources from up high, and then piping them down to villages. So this is where we lived. So essentially, just little huts, little tents, kind of out in the middle of nowhere. This is the kind of typical villages that we work on, and this is their water source. So this would be their water source, drinking water source for generations. So essentially, they just pull this out and walk for a while, fill up their jugs here, drink the water, get sick, and yeah. So essentially, that was it. So what we try to do is change that. So we'd find sources up in the hills of clean water, and we'd have the water kind of come down. We'd build a sedimentation tank, reservoir tanks, and then feed kind of water to 15,000 people. Tap stand. So this is all, it was all kind of volunteer work and stuff, so it just kind of shows the engineering. I mean, yeah, you can work for either a corporation or even some design outfit or construction, project management, but if you are really interested in development work, it's probably one of the most valuable skills you can know. I mean, engineering, medicine, nursing, kind of any of these things, social work are all super important for development work. Just kind of a typical design view. So this is just showing what happens when we find a spring and we have to protect it. So you dig down to where the water bubbles out of the ground, and then you have to protect it from things like cattle grazing around it or trying to contaminate the water, that kind of thing. So yeah, so you create a swale so that captures the water, you pipe it down, and then you cover it all with a whole bunch of plastic to kind of keep it from getting contaminated. And this is kind of the end, what a final project looks like. You can still pull water out of the pipes, and there's also all these underground pipes that are feeding this water out. And just an example, reservoir tanks, so nowhere near the technology we have here, but it still is very effective and so much better than what they had. And a tap stand. So essentially these tap stands are located every, I don't know, 150 feet or something like that, so then it's always in range of villagers. So essentially that's all the bulk of it I had. I don't want to kind of hit you with a ton of technical stuff or all that, but I'm hoping some of you guys at least will have some questions on, I don't know, engineering stuff in general. Yeah?
How much do you make a year?
How much do I make a year? Well, I will give a bit of a range. So essentially when I started, an engineering starting salary, depending on what you're working in, between like 50 and 60,000 a year. And it will, man, maybe go up by 3 to 5% a year. So after you're working for 10 years, you should be at between 80 and 100,000. It just depends on what company you work for. And, I mean, if you're going to work oil and gas, you're going to make a lot more money. If you're going to work mining, you're going to make a lot more money. If you're going to work somewhere like oil and gas in Saudi Arabia, you're going to make a lot more money. But if you really want to work in Victoria for the government, you're going to make a lot less money. So just kind of depends. Yeah.
Since you're part of the engineering, have you ever dabbled in any like blueprint designing or?
No, I haven't. I mean, essentially, actually, the designs that we do for ships are blueprints in a way. So they're blueprints for ships. So I haven't done as much like building and stuff.
But not like traditional like.
Yeah, so they are traditional. Well, they're traditional in the way that we do them in the computer now. So we do actually have in our archives drafting drawings, so all like hand-done blueprints. But yeah, it just takes way too long to do that now. So we used to have like a whole room full of drafters that would do everything by hand. And yeah, we just don't see that anymore. Yeah.
How long have you been in engineering for?
Like you're trying to deduce my salary and just working out the time. Man, I've been an engineer for about 9 years, 8 years. So yeah, so I did a master's for 2 years, which is great too. So.
Oh, that's a lot of money.
Where did you go to school?
I did university in Victoria, so UVic for engineering program there. It's a really, really good school. I recommend it, just because they have something called a co-op program. So I don't know. Actually, what grades are you guys in? Is this like grade?
12.
Okay, so 12 and 11, 11. Okay, so you got 10s all the way to 12. Yeah. So, so anyway, so yeah, UVic's a great school. It's small. It's a lot smaller than UBC. I know you have UBC Okanagan here, which is pretty good as well. But the great thing about UVic is that it's one of the few schools in Canada that has mandatory co-op. And if you're looking into university, I'd highly recommend looking into co-op. So what co-op is it's work experience. So you alternate between doing academic courses, so doing like math and physics and whatever, English and all that kind of stuff. And then you actually work for an engineering company if it's an engineering. You do co-ops in everything. You can do co-ops at UVic in English and computer science and all sorts of things. So essentially what that does, it gives you experience, which is hugely important for getting a job. And it also, you get paid. So you essentially can go to school for 4 months, work for 4 months, and then earn enough money to pay for your next school for 4 months. So it really helps, yeah.
What's your favorite part about your job?
Probably just solving problems. So you get some really weird problems, and then you kind of work with people and try to solve them. So also just changing the way things are done. So there's just people, often you find with every industry you work in, people do things a certain way because they've always done things that way, but this might not be the best way to do it. So ensuring you kind of get to question those, and then if you can prove that it's a better way of doing it, then people will change their minds. So, sorry, there's one question here I want to come to. Yeah. No, most engineering, no, I can't say for everywhere, but most engineering companies won't give pension. So it varies. A lot of engineering companies don't pay overtime. You're expected sometimes to work overtime, but they won't pay for it, but it's just kind of working with your salary. Other ones will pay overtime. A lot of them don't pay pension unless you're in government. If you're out as an engineer and a doctor and a lawyer, you're outside of the BC Employment Standard Act, so you don't have to get paid overtime, and there's not like restrictions for hours and stuff like that. So essentially, yeah, you can be expected to work a lot more. Yeah. Good question.
How much did your post-secondary cost?
Well, it's going to be different for you guys now because I'm sure it's going to gone up because I went to undergrad 15 years ago. But post-secondary, I kind of budgeted $12,000 a year in all expenses. So that was tuition, rent, and all that kind of stuff. So I had to pretty much save $6,000 for every 4 months that I was there. And if I was only going to school 8 months, then it was 12. But yeah, so it's kind of, yeah, 6,000 every 4 months. So I don't think it's gone up a huge amount since then, but maybe you'd have to budget 8,000 for 4 months or something. Yeah.
If you could change one thing about your job, what would you change?
Oh man. Yeah, I don't know. I really like my job, and I like the people I work with. I think that would be the biggest thing is that if I didn't like the people I work with, I'd change them. But yeah, I like the people I work with. I mean, I think I would like, I have a bit of a weird arrangement. So the company I work for is in Vancouver. Pretty much all the people who work at the company are in Vancouver. And Vancouver's very unaffordable, so we moved to Summerland, and I work from home mostly. So probably the one thing I'd change is I'd actually like to live in Summerland but still work in the office, because it's nice working with people rather than just working at home. But I'd rather live in Summerland and work from home than live in Vancouver and work in the office. So.
Would you say, so like in high school, at what point did you say, yeah, I'm a problem solving, that kind of a guy? When were you, those thoughts going to your
Yeah, I'm a bad example for this because I knew I was going to be an engineer since I was like 5 years old, and I was very like single-minded in it. I didn't even know what it was.
Well, and some of those, what were some of those characteristics? Like putting things together, taking them apart?
Yeah, definitely. That was it. So essentially just loved fiddling with things. So loved building Lego, loved solving problems, loved kind of working on my car and stuff like that in high school. Just any of those kind of mechanical things. Even you don't have to be good at those things to go into engineering either. So yeah.
Do you ever take apart anything your parents or like something like, you know, take apart your mom or dad's phone or?
I didn't do my parents' phones, but in engineering school sometimes if people had cell, and maybe you should think about this here. You can't do it with new phones as much though, but if someone left their cell phone somewhere and it was ringing obnoxiously over and over again, then usually we just disassemble it into its smallest pieces and spread it out like around the lab. So and the person to come back is reassemble it. Or if people fell asleep in class, you take their phone and put it on them and then phone it. So then they would wake up in class and freak out. Sorry, Alex.
What's for your undergrad? What's that like? What's school like? I have a few friends that did their engineering degrees while I was doing mine, and intense.
Yeah, so engineering for undergrad is pretty brutal. It's pretty intense. So at UVic, if you do co-op, it's 5 years. It's a 5-year undergrad. If you do UBC and you don't do co-op, it's 4 years. So you can do that. But it's pretty intensive. So when I was at UVic, So engineering started first year, 260 people in all engineering. After 4 months, we were down to 150. So essentially 100 people just drop out in the first 4 months because they just don't like it or they don't really like it. But it's really math focused. It's really, the first like year or two is just so theory focused that you don't get into the really interesting stuff for 3 or 4 years. You kind of press through that and then it gets a lot better. But if you are going to go into, I'll take your question in a second, sir, but if you are going to go into engineering, if you're thinking about going into engineering, I would strongly recommend you take calculus in high school because it's not mandatory. You can not take calc in high school, go into university, but man, the calculus you get hit with in university is so much harder than the stuff here. That's a stumbling block for most people because you are actually using calculus in almost every engineering course you're taking, whether it's chemistry, physics, the math ones obviously. Like any course in engineering almost involves calculus. So if you take it in high school, it's a way more gentle introduction to calculus. You can kind of get some help from a teacher and all that kind of stuff, and then you can actually kind of jump into calculus in university. It's not nearly as hard. So just it's a bridge that makes them so much easier.
Brendan, can you talk a little bit about the different types of engineering that there are out there? Just so they have an idea, because I think a lot of students just hear the word engineer and they don't really have a...
So there's tons. So at UVic, there's not as many. So essentially it's like mechanical, so mechanical engineering. So mechanical engineering is the design of anything that moves. So it'd be things in a car or ships or planes, like anything that moves essentially. Civil engineering is kind of like anything that doesn't move. So roads, bridges, buildings and all that kind of stuff. Civil engineering, houses. Chemical engineering, so it'd be like pharmaceutical and all sorts of chemical concoction kind of stuff. Mining engineering, that's just pretty obvious. Those are kind of some of the big ones. There's a ton of other ones that kind of fall underneath those. So there's computer engineering, so you actually can learn how to design, like how to build computers from scratch. So actually the whole circuit boards and all that kind of stuff. Software engineering, so do all the programs. There's a huge area, but a lot of these are foundational. So mechanical engineering is foundation for getting into tons of other types of stuff. So, yeah. Yeah.
Do you find you need your master's for many engineering?
Yeah, so it's a good question. So I know it's a long ways off for you guys if you're thinking about masters or not, but I would say masters if it's done with a goal in mind, like if it's done with a job in mind that you want to do, it can be extremely valuable. Because like, picture this, so you finish your undergrad in, let's say, engineering or whatever, any program that you do, and then you started a company, so let's say an engineering company, and you get stuck pretty much doing a lot of the jobs that no one else wants to do right away. So you have to work through that. So all the more grunt work and all that kind of stuff, you work your way up. But if you do a master's degree, you get specialized, and you get knowledge in an area that no one else has much knowledge in. So if it's valuable, then essentially you get leapfrogged right into like a really niche role in a company, and then it can be incredibly valuable. So say master's degree for the right topic is very, very valuable. But there's a lot of people who use those master's degrees as well, so they don't do anything. Yeah. Oh, Brendan has it at the beginning, but that's one of the questions on the yellow sheet. Yeah, and smoker, S-M-O-K-E-R for last name. Yeah.
What are some of the challenges that you face within your job? Like, what do you think are some of the hardest steps to tackle or create?
Yeah, probably the hardest thing is the constant pull. So as engineers, we're bound like ethically. So like we're bound. So we have like there's a whole governing body in British Columbia that governs us as engineers. So like we're bound to hold paramount the safety of people and hold paramount the safety of the environment and all those kind of things. So, but let's say those can sometimes come in conflict with, let's say, how much money your company can make. So let's say, hypothetically, your company designs something, puts it out there, and it's actually unsafe. And you find out as an engineer it's unsafe and it potentially has the risk of like hurting people. Well, if you go and report it, then the company's going to lose a ton of money because they're going to have to kind of recall that item. But if you don't report it, then people can get hurt. So there's like famous examples of this. So Ford has an example of this. They did the Ford Pinto like decades ago. So they designed this car. So it's supposed to be an inexpensive, cheap car. Well, the problem with it was that they found after it was already built and out there in the market, people had them, is that if it got rear-ended, the car squished so the doors jammed so you couldn't actually get out. and the gas tank punctured and the car exploded. So essentially, you had these cars getting rear-ended and catching on fire and exploding and killing people. Ford knew about this, but they decided rather than recall them because it would cost so much money, they figured they would save money by paying out lawsuits of people who died rather than actually recalling them. So that's like a brutal, terrible ethical decision that a company made. And so as an engineer, it's like we're duty bound if, let's say, we're at a company that faces the same decision, that we report it to the company. If they refuse to do anything about it, then as an engineer, we have to actually report it to another authority and go behind our company's back in a way. So there's sometimes, it's not to that extreme, but there's often tension in the company of like, if something's borderline, you're like, oh, I don't really feel comfortable with this as an engineer, but the company's like, well, you really need to do it because it'll make the client happy or not happy. So there's certain lines you have to draw as an engineer saying that, like, no, I will not approve this design or I won't release this. And then that can cause all sorts of friction within your own company because they're the ones paying you and you're saying, no, you won't do this. So that's something that comes up sometimes. I mean, we have a good company that deals with it, but yeah, it's constant friction between the engineering and the sales side of it. So, yeah.
Aren't there, do you know, or could you tell us some of the engineering, you know, it's like a senior class before it graduates, don't they do some sort of, I don't know, not a prank or an engineering feat?
UBCO car usually.
Oh yeah,
UBC
yeah.
car.
I think the last kids that did that at UBC got arrested. So,
Yeah.
but yeah, they used to hang a car off the Lionsgate Bridge. So they would, just push a car off the bridge with a cable, so then it would be suspended over the Lionsgate Bridge. So, yeah, it's pretty extreme. The last ones that did it, I think were caught partway through doing it. They pushed the car off and it hung there, and then the car fell into the water. So I think the kids got in serious trouble for that. So I don't know if I'd recommend that, but yeah, there are some engineers that are a bit crazy.
Or there's not there's not an official, like, you're supposed to create something for your final, not a prank necessarily, but something.
Yeah, no, there are final projects, but they can vary. So like we've made underwater robots, or you made like a robotic bicycle, or you make, or it could be sustainability, so you could do like, very fuel efficient buildings, but so it's all sorts of cool things.
I don't know, sorry to keep talking, but I don't know if you're aware, so I know that we have some students in here, plus some with Penn High, that they've been given a grant to create, they're going to enter a competition. And I was just talking to Mr. Laguerre about it last night, and I don't know if we know that we have you in Summerland as maybe someone to confer with.
Yeah, maybe. I don't know how good I'd be.
To just maybe come in and have a chat with them, because under a very short amount of time they have to create this project to take to competition.
Yeah.
And once they're committed, they have to go. So.
Yeah. Yeah. Well, yeah, you can definitely talk to me about that, but yeah, I don't know how helpful I'd be.
Oh, I'll bet. You might know some people will be helpful.
Yeah.
Brendan, can you talk a little bit about of what you know anyway, as far as the job market is concerned in the way for engineers right now?
Yeah, it's a bit unpredictable sometimes. For some reason, the job market right now is pretty hot. Like the economy for engineering is really busy. I don't know exactly why it's so busy right now, but yeah, there just seems to be a lot of more projects going. We're really busy. We have lots of ships being ordered. There's just a lot of development right now around the world. So yeah, the market, I mean, generally in engineering though, the market's pretty good because humans always need more bridges, they always need more cars, and actually the big one coming up is we need to be able to do things more efficiently, like more sustainably, reduce emissions, reduce pollution. So essentially all those things are going to be solved by engineers. So you've got climate kind of activists and scientists are really pushing for change, which is good. We need that change, but it's going to be engineers who actually figure out, okay, how are we going to generate electricity by producing less emissions? How are we going to drive around and produce less emissions? So yeah, these are all big things that we solve probably by engineers.
With your company in particular, have you guys been looking at, is it dependent on the customer as to how efficient it's going to be or how sustainable, things like that, or do you guys take that into account when you're working on designs and things?
So it's shifting right now. So essentially it's taken into account by the customer usually. So if the customer says, I want the cheapest boat possible, then we'll do like a diesel, just a traditional diesel boat, so you'll burn diesel. If the customer says that, okay, we need an efficient design for just our image or marketing, or we actually are concerned about the environment, then we'll come up with a more efficient one. Actually, the big thing that's changing now is regulation. So in Europe, there's like a regulation coming out in the next 10 years or something that they have to reduce pollution by 75%, which is a massive reduction. So essentially, customers don't want to do this, but if they're forced to by regulation, then we have to solve that problem as engineers. So that's going to lead to, actually, I think some big innovations in ship designs. You're going to have like fully battery-powered ships. You're going to potentially have fuel cell ships. You're going to have maybe methanol ships and all these kind of things. So everything now is pretty much all diesel. It's just the normal fuel for ships. So yeah, that's kind of the way it goes. But rather than, I mean, engineering, just a question for you guys. Are any of you guys involved in, like, or interested in environmental science? You guys wanting to go into like environmental protection, or is that not really your guys' wheelhouse right now? Yeah. Yeah, that's right. Let's just burn the environment.
Any other questions for Brendan? Had a lot of good questions, you guys. That's great.
Yeah, I got one more here.
Okay.
Yeah, I mean, just the people I work with, solving problems. Yeah, the flexibility, being able to work from home and travel. So I was in Scotland recently. I'm going to New Orleans in a couple weeks. I've been on to Australia, Wales, Vienna. So yeah, I mean, a lot of times you guys travel. So, yeah, but yeah. Yeah, we get benefits. We get some dental coverage. We get like some, I don't know, general medical kind of package things. So things that cover like physiotherapy and massage and all that kind of stuff. But, yeah, it's just kind of like a small kind of benefits thing. It's not like a more comprehensive benefits package. So, yeah, mostly your benefit is your pay. Yeah.
Is your side of like computer fluid dynamics, is that actually like very different job?
It's not physically grueling. It just can be a bit mentally tough. Yeah, we're working with like a bit more complex than the math side. Like if you go to university, you take a bunch of calculus, you'll probably never use it again for the rest of your life. But yeah, we took calculus and we're using it quite often. So yeah, so it's a bit grueling on the mental side. But yeah, physical, no. We just sit in front of a computer.
Never have to use any physiotherapy.
No, it seems. I mean, I'm sure some people maybe should, but it's more like if you get injured doing something else outside of work. So, yeah. I mean, if that's kind of.
Any other questions, you guys? Last opportunity.
That's right. Yeah, I'll be gone. I'll probably never see you again. So.
All right, let's give Brendan a big round of applause for taking time. Okay, as we've said before, you guys, we're bringing in all these speakers for you so that you get to hear firsthand about their experiences, whether it's through their schooling, the companies that they're working for, or if they're working for the government, things like that. So as we're hearing from these people who are taking time out of their schedules to come in and speak with you, please, if you have questions, even if it's an area that maybe you haven't really thought about, it might be something of interest to you, you haven't really given much thought about it, but ask those hard questions, right? Because it's really important as you're considering moving forward in a particular area, or just exploring the different options that are out there, okay? Later on this week for the linear classes and of course Miss Grant's classes on Wednesday. Wednesday we have a pharmacist coming in. He's going to talk a little bit about his experiences in pharmacy. What's that?
B block or tutorial?
That'll be in B block. In B block. In B block. Yeah, good question. Okay. And then of course Miss Grant's class. We have another speaker coming in tomorrow, which is
City worker, HR City.
yes, someone from who works for the City of Penticton in Human Resources. And so Miss Grant's class will be able to hear from that individual tomorrow. Okay. Stay with me. Before we part ways and head back to our classrooms, there's a few things we need to take care of. Number one, if you're on a folding chair, you need to put that back on. Don't move yet. Don't move yet. You need to put the folding chair on the rack by Ms. Millington. Make sure it is stacked well. If you are on the regular library chairs, we need to move the tables back around the library so that it is set up as it normally is. Okay, and then we will head off to our respective classes. Okay, again, thank you. Let me just kill that.